Hello there, my name is Mr. Evangelista, and welcome to another episode of Evangelista Science. Today we're going to finish up our lecture on 3-2, talking about periodic trends as part of the wonderful iBechem SL curriculum. So today we're going to be talking a little bit about metallic character. Okay, so metals are very good at conducting electricity. They are also malleable and ductile. But since they are able to conduct electricity, this gives us a kind of insight into what their properties need to be. So for one, they need to have a low ionization energy. Remember, this is the energy needed to remove an electron. So since they're able to conduct electricity is conducted by moving electrons, those electrons need to be easily removed. They cannot be bound really tightly. So we need to have low ionization energy, and we need to have low electronegativity. We need to have a low attraction for electrons because, again, we are transferring or conducting electricities in metal. And so what this means is our trend is going to be going from left to right. It's going to be less metallic, because when you're going from left to right, you are increasing in ionization energy and electronegativity. We want those to be low. Furthermore, going down, we are going to get more metallic because we are decreasing ionization energy and decreasing electronegativity. Let's talk about melting point. So melting is a process of going from a solid to a liquid. And so what we need to do in melting is to break these kind of forces that are holding this solid together to make it into a liquid. And unfortunately, it's not as easy to just say a trend. There are some exceptions. So let's take a look. For the group 1, these are metals, alkali metals. It's going to decrease down a group. Why is that? So if we see here, these are poorly drawn protons here. And we'll talk about this more in bonding in chapter 4. But how metals are bonded together is that they have a bunch of positive charges, and these electrons are kind of free to move in between all of those positive cations. And so when the alkali metals are smaller towards the top of the group, it's going to be really hard to melt them because they are a lot closer to these electrons. Remember, as we go down a group, those shells, those distances to those outermost electrons are going to increase. But at the top of the table, these distances are very close together. And so they're going to have a stronger bond, and so it's going to take a lot more energy to break these bonds since they're so much closer. Now when these electrons get further away, because we're going down a group, the amount of energy that we need is going to decrease. So the melting point is actually going to be lower. And that's because we have a far greater distance and a weaker attraction here for those electrons. Now with group 17 halogens, it's the complete opposite. It's going to increase down a group. And so something like chlorine will have a higher melting point than fluorine. It'll be increasing going down the group. We're going to talk about London dispersion forces more later, but just know that since we've got more electrons in chlorine rather than fluorine, we're going to have more forces, London dispersion forces between these. Now for group 17, these are no longer metals. These are going to be covalent compounds. We'll talk about that more again. Sorry, I keep saying that, but we're going to talk about a lot in chapter 4. And hopefully it kind of brings it all and makes it all make sense. Brings it all together and makes it all make sense. Now, a general rule for melting is that it's going to rise until it reaches group 14 and then fall until it reaches group 18. So it's going to rise until group 14. That's because that's about the time when we hit this kind of giant covalent structure. Again, talk about it in chapter 4, and we're going to fall until we hit the noble gases. Makes sense that it's very easy to melt the noble gases. If you notice, on the right side of the periodic table, we have mostly gases, and on the left side of the periodic table, we have mostly solids. And we see that trend here. Second thing we're going to talk about just real quickly, chemical properties. These should be pretty easy. Group 1, the alkali metals, they are conductors, low density. They react explosively with water. And the lower you go in the periodic table, the more reactive they are. So lithium, reacts with water, but it's kind of slow. Sodium is going to react explosively, potassium even more, and francium is going to explode with water. And they're also going to react with nonmetals to form ionic compounds. We'll see that later. Group 17 are the halogens. They are also highly reactive, but instead of the downward being more reactive, like francium, going up is going to be more reactive. So fluorine is actually the most reactive halogen. And that's because of a high electron affinity. We've got a +7 effective nuclear charge with those group 17 halogens. Group 18, the noble gases, the cool kids. These are going to be unreactive, monoatomic. These are existing as single atoms compared to, let's say, the diatomic molecules, the Brinkelhoff molecules, and they're going to have a stable octet. So those are the three groups that you kind of need to pay attention to their chemical properties. Last thing we want to talk about is the bonding of period 3 oxides. What the heck is that? Now, this is hopefully going to make a little bit of sense, but I promise you it will all come together when we talk about oxidation numbers and acids and bases and ionic compounds and covalent compounds, but we're going to introduce it in this chapter. So here are all the period 3 elements. And oxides mean that these are bonded to oxygen. Now, we are going to talk about later how to write the ionic formula for these compounds, but these first 3 are going to be ionic. The reason that is because it's a metal with a non-metal. Each of these is a metal and a non-metal. So these are going to be our ionic compounds. Starting here, we've got our covalent compounds, except for argon there, which is a noble gas. This means that we have 2 nonmetals. So nonmetal, 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 and so on and so forth. And it turns out that when you mix these with water, so if you mix sodium or magnesium with water, what you get is a base. When you mix these two with water, you actually get a base. Aluminum's kind of weird because it's called amphoteric, meaning it has basic properties as well as acidic properties. But these covalent compounds, when I mix these with water, I actually get acids. So I'm going to get here P4O10 phosphoric acid. SO3 is going to make sulfuric acid. Now, unfortunately for these are just, the formulas are weird. And this is something that you kind of just have to memorize, the formula for these covalent compounds. But these we can figure out with a rule, which we'll talk about more when we talk more in depth about ionic compounds, which again are metals and nonmetals, and covalent are 2 nonmetals.